Hello, I'm Richard Hooper. I'm the Publishing Director of the Satellite Evolution Group. I will be the host for today's event. I'm pleased to announce we have over 180 attendees from around the world, so welcome everybody. I'm pleased to introduce this interesting webinar brought to you by Satellite Evolution Group and GVF and sponsored by Benchmark, a leading innovative technology, engineering design and world-class manufacturing company. Today's event is entitled Satellite Systems Optimization, the next frontier in size, weight and power. And this event is going to answer how this can be achieved through the twin pillars of very high density integrated circuits and new methods for embedding COTS components. Now, we're lucky to have two great speakers, Brian Sinclair, Senior Engineering Manager for PCB fabrication and microelectronics manufacturing at Benchmark Phoenix, and Mitch Gibheim, who is the Technical Business Development Director for Benchmark's high performance computing and next-gen telecommunications market sectors. Now, I think the audience has heard enough from me, but I will be back to ask some more questions later. So over to you, Brian and Mitch.
Thank you, Richard. Good morning, everybody. I'd like to start off the presentation with just a short introduction, which Richard has already actually been so kind to do. Both Mitch and myself have been with Benchmark for quite some time and are both serving in the engineering categories here at Benchmark. We'll be our speakers here today. To myself, I'm a senior engineering manager here in the Phoenix location. We're a combined facility with printed circuit board manufacturer, so-called Micro E division, which does a number of unique packaging opportunities, and also a unit which is working on surface mount technology, sort of essentially the core business of Benchmark. I joined Benchmark actually here in 2020 after being with C-Corp Group and with MST, both two Swiss companies that are higher end manufacturers of printed circuit boards in Europe. Been with doing printed circuit boards for about 27 years, mostly with high-rel applications, medical applications, and space-based or defense-related articles. I did my initial stint in engineering with a degree from Cornell University, and have since that time just been essentially working in the aerospace, medical, and PCB fields. Mitch has been with Benchmark as the long-termer here for 25 years, essentially, and has done the full gamut of the engineering circuit here with Benchmark, starting off as a project engineer, elevating to an electrical engineering manager, and eventually serving as a product development engineering manager. He holds a Bachelor of Science degree from Milwaukee School of Engineering and has his master's from U, Wisconsin. Mitch is also, as you can see, an avid angler, and has got especially lucky here with a prized, I believe, sturgeon there, Mitch. So congratulations, looks awesome. So just maybe a quick overview as to what the presentation is going to include today. Just a short overview of just Benchmark and who we are and what segments of the business that we operate in. Then maybe a quick overview as to what the newest motivations are in launch systems and what's really driving the industry, particularly like to LEO, to low Earth orbit satellites, and how that is affecting our industry essentially here in electronics as well. Try to present to you here is also some of the examples of circuit densification and how that operates within achieving the swap reduction that satellite manufacturers are hoping to achieve. Going into more specific elements then with embedding components and hybrid assemblies. And Mitch will end this part of the presentation then with a couple slides on the mobile ground terminals and how at Benchmark is active in that area. So first of all, maybe just to benchmark a little bit, Benchmark is a company of about 10,000 employees, I believe, worldwide. Essentially have a market capitalization of right around $1 billion. It's been a household name for high reliability applications for quite some time. And over the years, in particular through the high frequency LARC division here in Phoenix, we represent a number of the, I guess you could say, the disciplines which encompass the benchmark name and are under the benchmark umbrella essentially of capabilities. Those include design engineering solutions and components. We have a very strong new product introduction support capability. PCB assembly has always been our mainstay and is probably how the market knows Benchmark the best. But you can also see represented in the facility here in Phoenix, in particular, supporting structures. For example, in the precision mechanical segment, that's also serviced out of Minnesota, I believe, as well. But from supply chain management, systems integration, all of these items are key to a vertically integrated organization such as what Benchmark is in delivering a product from front to finish. In other words, a key turnkey solution for high reliability and specialized applications. So markets, obviously, as you can imagine, are then multifaceted. Primarily, I would say that our markets do rest in aerospace and defense at this point, but we have some very notable and very strong activities also undergoing in computing, industrial, telecommunications, medical, and to maybe a lesser extent semiconductor equipment. But all of these are very much growing fields where we hope to gain additional footprint in the years to come. So one of the areas that Benchmark has certainly been active in over the past decades has been in satellite communications. For many years, Benchmark has supplied the industry, with transmitter and receiver modules, gyroscopes, things that are the essential subsystems of any satellite aggregate. So it's in particular with our strong presence also in doing different kinds of RF testing, has been, I think, a go-to feature of our customers want to work with Benchmark. Our design group is very familiar with the design, the environment of space, and as such, has developed their design rules and their ability to manufacture designs or come up with designs that are suitably ruggedized for the application of space, but also applications where particularly ruggedized scenario is required. So, for example, battlefield applications, handheld transmitters, things of that nature, where you just simply have a no-fail criteria being placed upon the product. But one also segment that is of shown particular growth is in RF filters through our Tijuana facility. Has been quite strong lately and has always been a strong partner for interplanetary applications for the low Earth orbit and geosynchronous applications. Focus again there on the environment design for the environment of various levels of being able to do thermal shock, temperature exposure, vibration testing. So the standard shake, rattle, and roll, I guess what you would commonly call it in the aerospace testing industry. So maybe taking a 30,000-foot view here just for a second. There have been some major developments in how satellites are being approached, their design. If you look back at the very early stages, I guess, of satellite manufacture, say primarily in the 60s and 70s, you're certainly looking at a very brute form of by comparison today, on the design technology, and even through, you could say, the 80s and 90s, relatively large configurations that requiring very large booster, support in order to deliver them to space. Certainly, I can look back into my past as well to a time when working in aerospace for actually sounding rockets and small payloads, and the challenge at that time already being how do you maximize the payload fraction for any given booster, or what will allow you to actually use a smaller boost vehicle to achieve the same result. So certainly there's been an awful lot of wants over many years to try and get a fundamental change in the size, essentially the size, weight, and performance, the swap essentially of the devices being delivered, payloads being delivered into space. So one of the key attack angles certainly is to say, how do we reduce the redundancies that are in current systems that are there essentially because of the high cost of what had been for delivering satellites into space, and giving it the additional and triple assurance that all systems could work. If I can assure a certain reliability of the systems I'm putting up there, I can certainly reduce those redundancies, reduce again the volume and mass then of payload, which in turn reduces launch cost, and of course allows then a more rapid and a more cost-effective delivery of payloads into space. So you can actually do far greater number of those, or have a better hold on how to replace those systems once they age. So this virtuous circle obviously is something that is wanting to be exploited, and is the driver principally behind the idea to miniaturize, to reduce redundancies, and what drives essentially our need to develop ever better technologies to meet that need. So some of the basic ideas that involve that is, how do you reduce the number of components? How do you reduce the number of connections that are required by those components within the interconnect? And how do you densify anyway the smaller components? Do you add additional layers? How are you able to do this essentially, and what amounts principally to a printed circuit board? So the manufacturing strategy, at least in the substrates area, focuses on how do I densify the circuits that I need to manufacture. I can make use of the 3D space essentially of embedding components. And I might even choose to look at the functionality of the board itself and say, if I were combining different kinds of materials, can I gain an effective edge on the side on swap by doing so? So your classic rigid flex board is maybe a perfect example of that kind of hybrid assembly. Driving it maybe to a next level would be to say, do I mix materials? There are a number of options, I guess you could say, beyond just simply doing a rigid flex board. So here's a case study, maybe just for everybody to evaluate. We had a challenge here essentially of a customer who wanted to take a handheld communications device and reduce it drastically in size. So if you can see the picture here, essentially on the left, showing the original device, and with the application of all those items that we were talking about, essentially a higher level technology for doing, for generating the lines and spaces on the board, smaller pad sizes, smaller via sizes, utilizing in particular also the advantages of advanced material types like LCP that allow for a z-axis reduction in height. We were able to reduce the size of that communications device to roughly 1/6 of what its former size had been in X and Y. So just as a comparison, you see the white board at the bottom there, that is an LCP construction, same functionality as the larger one on the left. So in many instances, there's a possibility of truly reducing the size and weight, and possibly also increasing at the same time the performance of the product, simply by thinking about it in that direction of how do I accomplish it. So maybe one additional thing that's happened to be a benefit, and just looking at the material side of it, LCP is very much a virtually like hermetic material. So the benefit of this one happened to be that as a battlefield unit, it was, we gained the added advantage of the material being virtually hermetic and thus much more water resistant than the original device had been. So give you an idea just maybe on the scale of the change that we're talking about. This is a pretty good slide, I believe, like in showing, you know, what we're really talking about. Part of our printed circuit board manufacturing technology relies upon what we call a modified semi-additive process for doing the circuit generation. That's kind of a fancy term for saying that we have a special process that allows us to gain a tighter circuit density while not sacrificing on the circuit height. So that you still arrive with cross sections, in other words, even with very densely packed structures that are as small as 1 mil lines and spaces. We can produce that with a higher yield and with a higher, you know, cross section than would otherwise be possible with conventional applications of technology in the PCB industry. So this gives a kind of a relative, the two pictures give it a relative idea, I think, of just how this works out as far as size. The conventional technology, quote unquote, that I would see today is still 75 micron or 3 mil lines and spaces. And that's usually married with a 1 ounce copper weight, or right around 35 microns. What we're aiming and looking to make our mainstay here at Benchmark is with the modified semi-additive process is a 25 micron line in space, where roughly we're still maintaining about a 15 to 20 micron copper thickness. So actually the signal integrity that you get out of that kind of cross section, as well as you know, the miniaturization, obviously the device is what is a huge benefit for being able to redesign packages that are today in the more conventional technology. The picture on the right kind of shows just also the difference in thickness. Now, these aren't directly comparable in the sense that you probably could reduce the bar that you see at the bottom right at the 3-inch mark. It shows like the conventional technology with ordinary rigid materials, and the caliper is showing you the thickness of an LCP board that actually had the same performance as the one on the bottom, but was only 8 mils thick. So getting maybe into the idea of LCP a little bit more, because it is really certainly at the center of a number of the solutions that we like to provide here at Benchmark. I mean, it's an excellent material just in and of itself from an electrical standpoint. It has awesome performance, even up to very high frequencies, as high as 110 gigahertz. We've supported applications from customers that were operating as high as that. The LCP, given being that it's a flexible material, is then also very much usable for rigid flex applications, so that you can make best use of volume considerations when essentially looking at your packaging. So we utilize it in that sense, or it has an advantage over a lot of the other high frequency capable materials, in that that are all rigid, and that you can actually make you know, a rigid flex board in that sense with LCP. I mean, a lot of the RF characteristics, you can say simply the performance level of the LCP versus more ordinary materials, has allowed our design group to often reduce the number of components on the whole as well. So there's a multi-tiered improvement, I guess you say, in working with LCP, and also opens up an envelope of solutions that otherwise would not be there. And again, I'd already mentioned like the waterproof nature of it. It also happens to be a pretty high temperature capable material. So in this grand scheme of things, LCP combines a wonderful set of performance variables, especially for high frequency applications. So this was kind of an example of a very first level embedded project that we'd been working on. We essentially took various forms of passive, but also some lower end active components. And we're looking to actually embed them within the LCP structure. So the cutouts that you see in the LCP marked by that brown perimeter essentially were cavities that were cut into the Z-axis of the board. Where you can either pre-cut those with a laser to pre-prescribed depth, or you can also ablate the surface in a so-called skiving operation down to a lower level. This, of course, can be a huge improvement to the overall usage of volume in any device if you're able to actually use the material that's part of the bulk of the PCB for embedding those components. You can essentially make the top surfaces smaller, thereby again reducing the size and weight of the unit, as well as the enclosure that aggregate requires then as part of the subsystem. So the other aspect of it too is that if you have sensitive components, especially ones that need to be radiation protected, this is also a means of being able to shield them from that kind of harmful influence. So with essentially this direction, you're able to combine yet another ability to better utilize the volume in any given device. And usually with that volume improvement, you also have a very large improvement especially in the weight of the enclosures that these devices are going into. Maybe another angle here, I guess, is one that is less often used, and that is to say certain parts of a module require different performance levels and or are intended to have different functionality. If built with the same material type or with the same technology, don't necessarily always provide an optimum result for what you're trying to achieve. So one of the angles that we've looked into quite strongly recently here at Benchmark is to say, what if we divide up the application according to functionality, and then pick essentially the material that is best suited for that functionality. Cases where you have a high frequency application, it might make the most sense to use the LCP. On another case, it might be that it makes more sense to use something like polyimide because of the higher dielectric strength. It's possible to combine these materials as long as you have the processing techniques, as long as you are aware of what the criteria are for successful, reliable construction. So we've been beating a pathway, if you will, trailblazing here a direction to try and get a little bit more in that, unlock, you could say, the potential of combining these materials and then designing those specific subparts of the system with a specific material in mind. So, and again, I think it probably follows logically that it does require, it's the processing, manufacturing expertise that you need. And we're in the throes of developing a number of new processes to support this aim. Okay, so this was actually a pretty unique case study that we had, or actually it's a customer relationship that we have at the moment that is working out quite well. The customer originally had a space-based application where, unfortunately, with their own manufacturer, they were achieving only very low yields, and despite the fact, and of course, and it was very difficult for them to, beyond just the simple yield challenge, the device itself had some very high performance requirements, essentially being a space application that needed to survive for many years. The customer approached Benchmark essentially with the idea first just simply taking over the assembly portion of this, of constructing these devices. but soon realized that we had a knack, I guess you could say, for being able to not only to think beyond the only task that we were assigned to do, but also think about the periphery of what's going on and what the inputs are to our own processing. And within that time frame, a very close collaboration essentially had developed. Ultimately, I think it was also Benchmark's ability to provide very advanced testing techniques and also the capacity to do so. The design group as well, being able to analyze possible improvements for the device, that ultimately led to the point of the customer entrusting Benchmark with the entire manufacture and testing of this particular device. And at the moment is ramping up in its production volumes with a very high success. We're achieving first run yields of more than 90%. And I think we can certainly cite this as a success story of the vertical integration that we've worked very hard here at Benchmark to develop, and one which we would like to carry out to further customers with the same level of success. I believe this is now time for Mitch to jump in, and so Mitch, I'll let you take it away.
Sure, yes, sir, Brian. Thanks. So as Brian indicated, there's a lot of the technology that's that he's talked about also relates to the ground terminals, whether they're stationary or mobile. There's a requirement of high reliability and ruggedization and things, but there's also some differences, right? The ground terminals typically have a lot higher volume requirements, and with those volume requirements can magnify some issues if you have issues with those terminal situations. So if there's things like process controls or cost or test or other attributes that reduce yields or have challenges, then you end up with lots of challenges when you have the volumes increasing. So there's standard things like processes and things that you have to be concerned about, and in some cases the ground terminals are, the boards are just standard, the PCB technologies, so you have to just do standard DFX practices and standard IPC things to make sure that your systems are built to qualities and ensure the yields are up there. There's also other things that you can do, like automation, to increase and ensure reliability and repeatability. And in some cases, it's needed from a precision alignment, precision assembly standpoint, or maybe there's requirements from an automation standpoint to realize the ruggedization. So in some cases, the ruggedization means that the system needs to be sealed, or there has to be adhesive applied, or there's some other assembly characteristic that is needed, and automation can be extremely important to ensure that your product can meet the needs of the system and meet the needs of the environment. So a lot of those aspects kind of are similar to what Brian was saying, but are slightly different. Then there's other aspects of ruggedization, like failure analysis and doing leak testing and some of those types of things that might be needed from a ground terminal standpoint. Then there's two aspects of test. So there's just the general testing, like in-circuit and functional testing, and then a variety of environmental things. A lot of our customers are wanting us to do thermal shocks or humidity tests or burn-in tests, things along those natures to ensure reliability and ensure the product is going to survive in the field. But then there's the other aspect of tests where it's the RF, right? There's obviously an RF component for ground-based terminals and the communication aspect. So the RF aspects of it and the RF testing can be quite dramatic in satellite communication based on whatever bands you're trying to communicate with and what is needed for your product. So we build a lot of things in microwave communication and millimeter wave communication, and the aspects for testing those types of products are fairly significant. as well as the equipment and experience, right? Chambers and screen rooms and whatever the test equipment is needed, and then the calibrations requirements, and then actual testing the devices, and sometimes open air testing is requirements. So not only you have to test it in your environment of your manufacturing floor, but maybe you have to expose it to the sky so that it can actually make a connection to a satellite. So there's different aspects of, you know, the testing aspect that have to come into play. And a lot of that has to be kind of managed by your partner so that they have what's needed to make it successful, right? So I think in summary, I guess the main thing that Brian and I are trying to convey is you're the experts in your product, and you know exactly what you need to have done, and it's up to you to find a partner that you can trust to understand what you need to get done, the ability to do it, right? So get them involved early so that they can be involved with the whole process, that first bullet there of simplification and the whole 3D volume utilization, as Brian was talking about. So that aspect of getting the partner involved early and understanding what your needs are, so that you can work together and optimize and create a solution that's going to be the best solution for you. And then the RF is the other big piece of it. So experience with the RF band and communication bands that your product requires. So making sure that your partner has experience in the RF bands that you need to be successful with your product, and has experience with it, has been building products with it, has the knowledge to debug and build those products is also important. And then you know, that's kind of the core design support and product support that's needed, but then it goes beyond that into the advanced manufacturing. So Benchmark has a proprietary shop floor control that manages all aspects of manufacturing, the traceability and genealogy of products, and managing components and serial numbers and test results and all those types of things, and gives customers access to knowing what's going on their manufacturing floor, so you can see what's going on with your products. So having a partner that has that abilities to manage the overall advanced manufacturing, whether it's the process controls or the RF testing or just the overall quality standards that are required for your product, is extremely important. I don't know, Brian, if you have things to add to that.
No, that's actually a wonderful summary, Mitch. I think that hits it right on the head. Actually, I think we're probably ready here for some questions. Richard, I'll hand it over to you.
Okay, thank you very much. Well, that was an interesting presentation, gentlemen. I'd like to kick this off. You mentioned in the presentation about some of the advantages to hybrid assemblies, but also that the manufacturing processes can be hard. How would somebody go about weighing those trade-offs and evaluating the risk?
Good question. Definitely, we always advise our customers to seek out our engineering group, essentially for the support with let's say a product they have at this time, and give us the opportunity essentially to evaluate that design and see where there are possible improvements, both for swap considerations, but also from a reliability standpoint, where we might actually be able to simplify the design and achieve essentially not just the size and weight reduction, but also hopefully an improvement upon the performance. So that would probably be the first level tier for being able to get answers to that. I think especially if you're currently working with more conventional materials and PCBs, if you're working with more conventional levels of components, certainly Benchmark has achieved an edge, I think, over a lot of our competitors in the utilization of what's really available out there. So there are new exciting combinations of technology that we would like to not only continue pursuing new opportunities with customers on, but also to continue to develop together with customers to achieve what they're looking for.
Right. Well, we've had a question come in from Fabian. He's asking, are you working with any kind of equipment, including optical, not only RF?
Yes, as a matter of fact, we have one particular product right now that's running through our facility, which is an optical rigid flex application, which is quite advanced, has some very high requirements on cleanliness, and is one that is certainly challenging us on a number of different levels. One that where we've gladly taken on the challenge and to see if we can't essentially replace an assurance of supply that the customer had with a current supplier that is unfortunately tuckered out, and where they're seeking our help and trying to get a supply chain set back up again. So we're essentially trying to combine essentially 2 years worth of development at the previous vendor into about 8 weeks. But we see the challenge and we're taking it on.
Okay. We just had a question come in from Michael Lukin. Do you have manufacturing facilities for space qualified satellite payload electronics in Europe?
Not in Europe, to my knowledge. Right now, it's been U.S. based, but we have been making greater inroads to trying to market ourselves in Europe. We have, locations obviously in Western Europe that we're operating out of. Most definitely, the European business segment is very interesting to us, and we'll be seeking out new partnerships there.
Right, going back to what you were saying in the presentation, we have a question here about the trend towards cubesats and other smaller satellites, relying on reduced requirement for redundant systems. But the question is, reliability and long operating life are still key for satellite systems. What's the reliability record like on m-SAP circuits, specifically with mixed materials and very dense topologies? How long have they been used in other applications?
As you would probably guess, the answer is not very long. And that might be the thing that has probably been the biggest hurdle to trying further grow this business segment, even though there is plenty of interest in wanting to go down that path. So I'm going to say that it's kind of a combination of, yes, there isn't a lot of actual experience on products that are currently deployed in space. However, there are a number of projects which are currently underway, being manufactured and being tested for their reliability here on Earth at first here too, and assessing what their performance is relative to known systems. So we're probably just a little bit early in the game to be able to do a apples to apples comparison to technology that's out there. But we know that we've achieved obviously the improvements in the size and weight, the performance issue we're measuring, the reliability we look to obviously try to measure with extensive testing, but the real life environment, I guess you could say experience, will only occur when more units have been deployed to space, right? Which we see, the next, let's say 5 to 10 years is doing.
So just staying with this for a moment, how do you weigh up the risks? What are the known risks in this? Well,
it's interesting that you mentioned that, because when you look at risks, like from a more system level perspective, there's a number of ways of maybe looking at that risk, like on a common assembly. If I have a typical printed circuit board, a rigid printed circuit board, for example, several of those boards interconnected with cables, connectors, each and every one of those components, each and every one of those interfaces contains a certain level of risk. Many of those interface risks that we were talking about there can be replaced with, let's say, a different approach in the technology. For example, let's say a rigid flex essentially replacing an assembly of cables that's essentially being made with connectors. You can certainly reduce the reliability risk that you have by replacing the connector with just a uniform part of the cable itself or part of the board itself, as long as that's been designed properly, obviously, to handle what it's supposed to on the signal or power or whatever what is being done, right? I think there's the other part of it too, and that is that sometimes mechanically, in particular, the reliability is more of an issue, given all the processing that might need to go into manufacturing it in that way. In the one case where it's just simply part of the printed circuit board, it's printed circuit board process that you're testing through for all other parts of that board. Whereas like for an assembly process that requires the connectors, you have the mechanical interfaces. So not just the component, but the interfaces, the process technology, all of that is working in as a part of the risk. So there are common measures that are used in the industry for measuring risk. For example, IST or D-coupon testing is, very common and very typical, and, currently deployed systems have likely undergone, well, at least the D-coupon case. IST is probably a little bit too new a technology for that, for most of those that are deployed. But the fact being that we can do apples to apples comparisons on that level and assure that we are at least performing as well as what the demonstrated yardstick of good reliability is. So
Okay.
in other words, we fully intend to support customers who are utilizing this technology and improving that reliability is at least equal or better than what has been put up there so far. I think the thing that is also to be recognized is that some products work better if they are smaller. Just the general the environment in which they are in shows an optimization in size to reducing the stresses on the product. One thing that for example, springs to mind is just an optimization on, for example, micro via size. An investigation that I conducted several years ago was one to see where was the highest IST reliability values where you could achieve them as a function essentially of micro via diameter. And the industry commonly accepted size of 75 microns was certainly not the optimum. The optimum was much smaller at essentially 45 to 50 microns. In going through a certain thickness of dielectric. So in a lot of cases, smaller is indeed better. And so for that size, we'll be looking for those optimizations and where they make sense.
Well, we've had a question come in.
Mm-hmm.
It's quite open. Can you provide any figure with respect to power saving for typical components you may have to work with?
Oh, bit of a difficult one. I can't name a certain number, I guess, to it. That'd be kind of a question, a great question, actually, for one of our engineering managers here in house, who could certainly provide a better answer to that. But we do routinely get the question as to how we can reduce the power requirements, quite obviously, just for the sake of again swap, but also for heat dissipation. So the one of the aims, obviously, and I think in conjunction with going with smaller feature sizes, is obviously the want to also reduce the amount of power that's being consumed as well. Power sources needing to be smaller, everything wanting to be a lower consumption. So, although I'm sorry I can't answer your question, I guess as explicitly as I think what the answer you're looking for, but we can certainly provide information if we have that available. We can direct that question internally.
Okay, Brian, thanks for that. We'll follow up on that afterwards with the person who asked that. Another question here on ground receivers. Cost is still a major issue, but due to the number of units being deployed, How many companies are hitting the cost goals while getting the reliability, performance, ruggedization that they want?
m-SAP, do you want to take that one, or?
Sure. So I kind of touched on that a little bit when I was talking about it. It's more of, like we talked about, as the volumes increase, that any issues with regards to yields and reliability and things cause some challenges. So the having opportunities to maybe add manufacturing automation that can help reduce labor costs and help increase reliability and increase your yields of your products. Also can ensure more repeatability as far as the assembly goes. Sometimes your product actually requires automation just based on the nature of what needs to be done. But sometimes it's just purely, it has so much intense hand labor that an automation would greatly increase and help the assistance in the manufacturing process. It also, could help a lot with the RF devices. So a lot of times having repeatable processes in manufacturing gives you more consistent output when you're generating products that have a RF nature to them. So that automation is a huge piece in it. The other thing is having a robust full suite of test solutions. So ICT and functional tests and environmental tests and tests along the way throughout the entire process. So you're not just putting it all together and test it at the end, and then if it fails, then what do? You have to make sure all the pieces will work as you're putting it together. That can help dramatically. I think that's probably the main things I can think of there.
Well, we've had quite a technical question come in. How do you handle stray capacitance or inductance in closed up RF miniature embedded connections?
Oh, okay. I'm going to say that probably one of the principal ways of doing this, we look at that, I would say, principally at the design level. The printed circuit board facility, for example, is supported with a design group, which is capable of doing a number of different simulations, including ones which go into straight capacitances, impedance, etc. One of the first steps in really looking at let's say an aggregate system, such as the one I think that you're approaching, is that we would essentially replicate the layout, if not already existing. We would, or if it isn't existing, we would create it, obviously, and then do that level of simulation here in-house and assure that those levels that are needing to be controlled are controlled in the level that the performance envelope or the spec of the device is requiring. To the more practical side of it, you could say that, well, I guess you could say that's even the design is in the end the practical solution here as well. Ultimately, the material sets that you're working with also dictate to a large degree how much those capacitances are going to matter within your circuit. The design rules that you decide to combine with the different material types ultimately has the play on whether or not those values that you're looking for can be achieved. So I'm going to say that probably the best way of answering that question is to say that we look at the system as a whole. We look to try and simulate the system as a whole. And we work together with the customer in trying to identify what performance parameters are of importance and what circuits, and look to find specialized tailor-made solutions, if necessary, even to control those variables.
Okay. Question here, all about standards. So are all of the design features you talked about in the presentation being able to manufacture within IPC design standards? If not, how do you ensure designs will be reliable?
I'm going to say that probably most of the rules that we apply for our design rules would also incur a simultaneous compliance with IPC 601, 3 or 8 as applicable. Class 3, which is typical for high reliability applications. Where that is not the case, then obviously it's an agreement between customer and ourselves. Often enough, there are special aspects to the design where you can't, for example, maintain you can't maintain the rule of IPC, but where the functionality of the board has precedence, right? So, for example, if I'm working with a very, very fine line structured device of 25 micron lines and spaces, my maximum copper in the hole might only be 18 microns. Let's say, given the performance profile for the device that is fully suitable, let's say for both for the signal integrity as well as power requirements, et cetera, but that would technically be a violation of class 3 because it requires 25 microns in the hole. So those are the things that we would identify. And to be honest with you, a lot of the miniaturization efforts that we have in that regard do require us here and there to make specific tailored specifications that lean heavily on IPC class 3 or just slight modification of those, but where they're in agreement with the customer. And then usually supported with some form of testing to prove out that there isn't a risk being built in because of that. So, but in general, yes, most of the devices that we have being manufactured here are built in consistence with IPC class 3.
Okay. A question that's come in is very general. The current world crisis, is it having an effect on component supply chains?
Yes, we've seen certain, I could speak now directly, let's say, to the materials used in printed circuit board manufacturing. There are some materials that are relatively difficult to get or have been. I think that we're just coming out of the slump, perhaps the worst delays that we've had in the industry. But there was, I would actually say some of the more common materials were actually more difficult at times to procure than the ones that are on the higher end of performance. So actually with respect to LCP, the formulation that we are using plus the adhesives that we were using actually never missed a beat as far as availability, and the supply chain was maintained. Others that were more common material sets out there, I'm going to say, ran into some real difficulties probably about 6 months ago. And those problems are now finally being alleviated. Otherwise, on some of the other components, I can only speak more generally, but I don't believe that it had been as severe as some of the delays that we'd seen on printed circuit board materials. Were actually, I think, a little bit more severe than even a lot of the components that we were needing for the assemblies.
Okay. I think we're jumping all over the bit here. We've got another question come in.
Okay.
With regards to what influences the densities you can achieve?
Sorry, I didn't catch the first part of that question. The first part, could you repeat?
Yeah, what are the factors that influence the densities you can achieve on the boards, the m-SAP circuits?
Mm-hmm. Excellent question. Major factors that influence that are the size of the board. In other words, there's a certain limitation where I can, just universally, achieve a 25 micron line in space with a reasonable yield. So the size of the board in X and Y, tends to be a limitation. Beyond, let's say, really a 4-inch square device, it starts getting difficult to have a universal, design rule of 25 micron lines and spaces. The other thing that it can influence, obviously, is the thickness of the dielectric layers. Usually, if you're combining very tight structuring, you're also wanting to have very small pad sizes, very small interconnect. And the aspect ratio of capabilities of filling a via with metallization are the limitation on what kind of thickness that you can achieve or what kind of dielectric thickness you can support. So those are probably the two primary ones I'm going to say that are out there that affect. There are ways around their circumvention possibilities there that with increasing layer counts and a number of other things, tricks of the trade, if you will, that we can employ to get around some sometimes relatively difficult little snags, but ultimately we have a very experienced group of people here working in printed circuit boards that have worked at at several different board shops, even internationally, have had the ability over those long tenures to learn quite a few tricks of the trade and a couple nifty solutions. So my team here is quite astute at being able to find the unique solution sometimes that's required in order to make it happen.
Well, thank you for that, gentlemen, because we've just reached our 60-minute marker. We haven't got any more questions come in, but I'd just like to say to the audience, if you have any further questions and you'd like to follow up with us afterwards, we'll be happy to respond. Brian and Mitch will be happy to respond. So I'd like to thank you, Brian and Mitch, for a very interesting hour's presentation. It's gone very quickly, so it has been interesting. I would like to thank Benchmark for sponsoring this event, and the video will be ready to view in the next day or two. So if you missed the part of the event, the video will be available. Before we go, I'd like to remind everybody that our next Satellite Evolution of GVF, entitled Satellite Network Solutions, Development and Evolution of Capability and Performance, will take place on the 25th of March at 3 p.m. I've just been reminded that you will be able to find the video of today's event at the GVF's website at gvf.org/webinars. And please go there and have a look. And we have all of our past webinars there as well. Gentlemen, thank you once again. It's been excellent. And thank you to all the attendees for joining us today. Thank you very much.